Hi, my name is Derek Decker, and I wanted to tell you a little bit about second order circuits. This is to help my students in ES 220, and let's go ahead and get started. So this is a series RLC circuit with no sources, and we're going to be considering a current in this direction called I of t. And what you'll notice is that if you apply KVL, Kirchhoff's voltage law, you'll have L di dt is the voltage drop across the inductor. You have R times I is the voltage drop across the resistor, and 1 over C integral from minus infinity to t of I dt, all sums to 0. And what we can do is take the derivative of that equation in each element, and that will give us the second derivative, d squared I dt squared plus R di dt plus 1 over C I equals 0. So from there we can make an assumption that if we let I equal a e to the st, then di dt, what happens when you take the derivative is the s comes out, so it's just equals s times I, and then you do it again, another s comes out, so d squared I dt squared equals s squared I, and so we end up with L s squared I plus R s I plus I over C equals 0. And of course, we can take out all the i's, just divide the whole equation by I, and we just get L s squared plus R s plus 1 over C equals 0. So you may recognize that as a quadratic equation, and that quadratic equation has roots of s equals minus b plus or minus square root of b squared minus 4ac over 2a. In this case, a is going to equal L, b is going to equal R, and c is going to be 1 over c. This is kind of a little c, and this is a capital C. And so when we do that, we end up with this equaling minus R plus or minus square root over 2L of R squared minus 4L over C. Now you can take this 2L and you can factor it back in, and let's go ahead and do some of that. So this ends up being minus R over 2L plus or minus the square root of 4L squared times R squared minus 4L over C, which then becomes let's see, plus or minus And that can be further reduced to minus alpha plus or minus square root of alpha squared minus omega naught squared, in which alpha, use a different color, equals r over 2l, and omega naught equals 1 over the square root of LC. So we can rewrite this equation here as just by first dividing through by an L. So that would give us S squared plus R over LS plus 1 over LC equals 0. And we can put in the values for alpha and omega naught. So that would give us S squared plus 2 alpha S plus omega naught squared equals 0. Okay. So what that says is when we solved for the roots, which was, looks like I erased those, but I can write those up again. S1 will equal minus alpha plus square root of alpha squared minus omega naught squared. And S2 will equal minus alpha minus square root of alpha squared minus omega naught squared. And what we have is solutions of the form I1 equals A1 e to the S1t, but we also have a solution of I2, which is A2 e to the S2 of t. And because they're both solutions, the total solution will be a combination of those two. So I will equal I1 plus I2 which will be A1 e to the S1t plus A2 e to the S2t. And so to take a closer look at what this might be in Mathematica, I have a model that I put together which you can take a look at, and we'll show it in just a moment. So what you notice about this particular interactive Mathematica is that you can see the two exponentials, the orange one and the blue one, and when you combine those two, when you add these together, this one plus the other one, so I've got them graphed 1, 2, and then together, and the sum gives you this green line here, which will depending on the magnitudes of A1 and A2, could start at 0, or you can see it doesn't have to be 0. So if I0 is not equal to 0, that's okay. The important thing is that you're bounded by these two exponentials that quickly decrease to 0. And depending on your boundary conditions or initial conditions, you will have whatever value is appropriate for the initial value of the current. And of course the slope at which it departs from there is also determined by the initial value on the capacitor. So for example, if you have 0 value on the current, but the capacitor has a negative value, then it's going to increase in that direction. Whereas if you have a negative voltage on the capacitor, it's going to increase in the other direction. But still, it's going to be trapped within these two exponentials.